We also see effects of gold nanoparticles on human cells. So these were colon cancer cells exposed to gold nanorods. These are a bit bigger than the spheres, but and like Vicky was alluding to, we have very good chemists that can make different size particles with different aspect ratios, and they can make hundreds of different coatings and so forth. And so if you start testing all these, you can look at effects on cell viability in this case. What's interesting about these particles is they're made with a surfactant called CTAB. And it turns out that the surfactant that's used to make the particles is what ends up causing the toxic effects, so it's not the particle itself. Okay, so this now adds another level of complexity onto the particles we study. So these are different aspect ratios, length to width of different size rods, and if you look at the CTAB coated rods, you see that cell viability is decreased. But when you actually cover that up with various agents that alter charge and other things, there is no cell viability. So this kind of goes back to what Vicky was talking about, was safe particles by design. Should we be focusing on trying to more carefully design particles that go into consumer products that may have less toxicity? So the problem with that, though, is just because they're designed for a consumer product or some biomedical application, they're not toxic in that setting. What happens to these now when they get out into the environment? And that may be a very different story. Okay. Something that doesn't get a lot of attention, which I feel is important, and others at USC who are studying this, are what about particle synthesis byproducts? Okay, so not only do we have to look at toxicity associated with the particles themselves, but what about some of the byproducts that may get out through wastewater or industrial effluent? Okay, so an example of that are carbon nanotubes. So they're produced through an arc charge discharge with metals, and you can see this is a electrophoretic separation on a gel, and you can see that these are single-walled carbon nanotubes right here, but there's actually two smaller by molecular weight products called short tubular nanocarbon, sometimes referred to as nanohorns, and some sort of fluorescent material that we have no idea what it is. But these are synthesis byproducts that come along with single-walled carbon nanotubes. And so do these synthesis byproducts have any effect on, with respect to toxicity? And the answer is they do, depending on what your assay is, right? So this is a study done by Lee Ferguson and Tom Chandler looking at effects of carbon nanotubes and their byproducts on a marine invertebrate. So these are little critters that live in estuarine environments and are in the sediments. Okay? And if you look at exposure to these are non-purified, so this has all the components in it, purified carbon nanotubes and fluorescent nanocarbon. I don't have the nanohorn data on here, but basically you can see that there's no difference in changes in this case we're looking at development between pure carbon nanotubes and the raw nanotubes, but look at the effect of the fluorescent carbon. Okay, it has significant effects on development of these little critters. Okay, so this is just to bring up the point that not only do we have these particles to look at, but what about their synthesis byproducts, which will likely end up in the environment as well. Another point I want to make is, do new materials influence toxicity of old materials? So there's a group looking at the interaction of carbon nanotubes with known contaminants such as PCBs and PAHs and so forth. And it turns out, and that's what this data shows here, but the take-home message is that they soar very highly to PAHs and PCBs, more so than they do to soot. Okay, so how does that change now things like bioavailability in the environment? These things get out into the sediment, which is where a lot of PCBs and PAHs are, and they're going to soar more tightly to carbon nanotubes than they do the sediment. How does that alter bioavailability to other organisms? And it turns out if you look at PCBs and some PBDEs, the fire retardants, the answer is it may alter bioavailability a little bit, but it actually seems to decrease some of the bioavailability compared to just the contaminant by itself. Okay. So unexpected finding there. And lastly, I'm just going to mention some unusual effects we've seen in freshwater fish model. So this is Medaka exposed to silver. Silver gets a lot of attention these days as antimicrobial agents and so forth. So these are very small silver nanospheres, about 4 nanometers, I believe. And these are fish embryos. You can see the embryo developing right here, and here's the yolk. And after 5 hours of exposure to silver colloid nanoparticles, you see that the embryo is basically disintegrated. This is a commercial product we use for testing here, which is no longer on the market. Okay. One thing I will say about this, as environmental toxicologists, we have to be a little bit careful because the dose we used here is very high. Okay, and it doesn't reflect what we think will be environmental levels of exposure. So this is classic toxicology, whack them with a real high dose of something and look if it kills them or not, right? But what happens when we look at lower, more environmentally relevant doses? Basically, to sum up this table, what we see is that there are more subtle effects at lower doses. And so we see things such as spinal deformities, which are fairly unusual, and things like edema and effects on the cardiovascular system that is extremely stage specific. So if you think about development having many different stages, this is a thalidomide's classic example of that, right? So women or embryos were exposed at a very specific window, and then you saw effects on the children. But exposure outside of that window didn't really seem to have any detrimental effects. So another thing that we have to be concerned with, and so this adds another level of complexity, is looking at stage-specific effects. If we do exposures to adult fish, we don't see any toxic effects of these particles. If we do exposures outside of these 2 stages of development, we don't see any toxic effects. Okay. So what does all of this mean as a toxicologist or a molecular toxicologist? It's not a very good answer, but it's the answer I have right now, and that is our understanding of the potential toxic effects on nanomaterials is, I think, a lot more complex than we originally thought it was. And we have a really daunting challenge, and so Vicki alluded to this with respect to risk assessment, and there's so many nanomaterials and byproducts, and classic toxicological paradigms probably need to shift more towards an interdisciplinary approach, which I think science already is, but this needs to include a focus on modeling and what she termed forecasting to try to get a handle on translating this basic science into some sort of risk of exposure. But how on earth do we do this? And that's a question posed because I have no idea how we even start to begin to do this, but something that I think we have to think about as, say, molecular toxicologists is, what is our responsibility into this? And then when you put in the public perception component, what is our responsibility to the public and how we communicate this risk? So, and I'm not going to show that because Jennifer already sort of mentioned that. But, and so I'd just like to acknowledge the nano-environmental teams, or these are the people responsible for all the research I showed, Research Triangle Institute, and of course the funding. So I'd be happy to try to answer any questions. I know it's probably a little different type of talk than we've been hearing, but yes.
I like these talks.